All right, section 9-7 is on integration of rational functions by partial fractions. The objective of this section is to find the integral of a rational algebraic function by first resolving the integrand into partial fractions. In the first half of this section, we saw how to do that. We saw how to take a rational algebraic expression and break it down into simpler rational expressions. And then by doing so, when we go to integrate, we just ended up using our logarithm to do that. So we're going to look at some more variations of that here in this second half. All right, the first variation here is dealing with what we call an improper algebraic fraction. And an improper algebraic fraction is just an algebraic fraction or expression whose numerator has a degree that's greater than or equal to the degree of the denominator. We have improper fractions when we're dealing with numeric values, when the numerator is bigger than the denominator, like 5/4 or 7/5. And likewise, we have that for algebraic expressions as well. So how do you deal with that? Well, you can use division to help you simplify this. You can use long division or synthetic division to simplify first. And then once you have it simplified, you'll have a quotient and remainder. The quotient you should be all set to integrate. That's just going to be a polynomial, so that we know how to integrate. The remainder, though, will be a fraction. So we can use partial fraction decomposition on that remainder if we need to. In some cases, we might not need to. We might be able to integrate just as is. All right, so let's take a look at an example of that. On page 463 in your book, they give us an example here of this integral, x cubed minus 9x squared plus 24x minus 17, and that's all over x squared minus 6x plus 5. You can see that it's improper because the degree of the numerator, that's cubic, so it's a degree 3, versus the degree of the denominator is second degree, it's quadratic. So it's improper because of the fact that the degree of the numerator is greater than or equal to, it's greater than in this case, the degree of the denominator. All right, so the first thing we want to do is actually simplify this, and we're going to use long division to do that. So let's refresh our memory here a little bit about long division for polynomials. To divide these, I take the denominator. I'm going to write that as x squared minus 6x plus 5. And I'm going to divide that into the numerator, which is the x cubed minus the 9x squared plus 24x minus 17. Oops, minus 17. All right, so the way that you set this up is you're trying to find out what you need to multiply this polynomial that's out front by. And in particular, I'm going to focus on the x squared part of this. What do I have to multiply that by in order to end up with this x cubed that I see right here? What do I have to multiply x squared by to end up with x cubed? Well, if I multiply x squared by x, that will give me an x cubed. So above the x term, I'm going to write just an x here. And now I'm going to go and multiply that x through this polynomial up front. And I'm going to write the answer down below this x cubed that I've got there. So let's go through that. If I take the x and I multiply by x squared, that gives me an x cubed. And then I take that x and multiply by the next term. By a negative 6x, will be a minus 6x squared. And multiply the x times the 5 will give me 5x. Now what I need to do is subtract these, so I like putting this in parentheses and then put my negative sign out front just to remind me that that negative sign has to get distributed all the way through the parentheses here. I'm going to subtract that from what I have up above here. So what do we get? I take the x cubed minus the x cubed, that gives me 0, which is my whole point here. I wanted to come up with what I had to do to eliminate that. So we've done it. Now I've got a negative 9x squared, and I'm subtracting a negative 6x squared, so that means I'm adding that on. So that'll give me a negative 3x squared. Then I've got 24x minus the 5x. 24 minus 5 is 19x, positive 19x. And then finally I've got this minus 17 minus, and there's no constant here, so it's just a minus 17. And now I'm going to repeat this process, but now I'm looking at, instead of the x cubed that I started with up above, I'm now looking at the 3x squared. And my question is, what do I have to multiply the x squared that's out front here? What do I have to multiply him by to end up with a negative 3x squared? Well, clearly that's a minus 3. If I put the minus 3 above the negative 17 there, and now I'm going to take that negative 3 and go through and multiply by this polynomial up front and write the answer down below here. So the negative 3 times the x squared is going to give me a negative 3x squared. The negative 3 times the negative 6x is going to give me a positive 18x. Negative 3 times the 5 is going to give me a minus 15. And again, I need to subtract these, so I'm going to put that in parentheses and put the minus sign out front. And again, that's hopefully reminding me that that minus sign has to go all the way through those parentheses. So I've got a negative 3x squared minus a negative 3x squared. That's 0. That was my whole goal there, was to eliminate that. We did it. 19x minus 18x. That's better known as just x. And negative 17 minus a negative 15. That's the same as negative 17 plus 15. So it's a minus 2. That right there is our remainder, because there's nothing I can multiply by in order to end up with, there's nothing I can multiply the x squared out front by in order to end up with just the x. I'm now below the degree of that number that's out front, or that polynomial that's out front. So this is my remainder. In fact, I'm going to write it that way up here. That my quotient is the x minus 3, and then my remainder is the x minus 2 that's down below, divided by the denominator, the quantity that's out front. That's the x squared minus 6x plus 5. All right. So just to make sure we're clear here, we're claiming that that fraction that I have to start with here, this rational expression, this guy right here, I should do this in a different color, this guy right here, and this guy right here are equivalent to each other. So if I was to take my calculator and graph those two, I would end up with the exact same graph. Those two are equal. So that's how I'm going to rewrite this integral they gave me. I'm going to rewrite them that way. Before I do that, I want to break this down even further. If I look at that remainder part looks a lot like one of these partial fraction decompositions we've been working with in the first section, or the first part of this section. So that's what we're going to deal with now. Let's take that remainder part and work with him. So I'll rewrite this. So I've got x minus 3, and then plus, I had the x minus 2 divided by, and then it was, well, I think I'll wait to, I was going to factor this, but I think I'll wait to factor it. Let's just rewrite them as is, and then we'll factor the denominator. X squared minus 6x plus 5. Let's go ahead and factor that right now. So the x minus 3 stays as is, but I can rewrite this as x minus 2 divided by, got to look for the factors of x squared minus 6x plus 5. Two numbers whose product is 5, but sum is a negative 6. That sounds like an x minus 5 and an x minus 1 will do that for me. All right, and now let's use our cover-up technique to help us evaluate what that's equal to. The x minus 3, the quotient stays the same. But I'm going to write this as some number over x minus 5 plus some number over x minus 1. And maybe I should highlight what we're doing here. I'm only going to be focusing on this part right here to get this here. All right, I'm not going to deal with the x minus 3 part out front. I'm only looking at that remainder section. So go through your cover-up technique. I'm going to cover up the x minus 5. If I cover up this x minus 5, the question is, what value do I have to plug in to make that 0? That would, of course, be 5. And when I plug that in the numerator, I'd get 5 minus 2 is 3. And in the denominator, 5 minus 1 is 4, so 3 over 4. So that numerator there is going to be 3 over 4. Oops. I guess it's okay if I put it in red, but I don't really need to. This is 3 over 4. Now do the same thing with the x minus 1. I'm going to plug in a 1, of course, to make that 0. So I'm going to cover this guy up. Plug in a 1 in the numerator. 1 minus 2 is a negative 1. 1 minus 5 in the denominator is a negative 4. Negative 1 over a negative 4 is a positive 1/4. Now you might recognize this. This is the same as our last example from the first half here, or at least the denominator has that same thing. All right, so now I should be able to integrate this. Going back to what the original problem was. The original problem was to find the integral. So let's do that. We want to find the integral of x minus 3 plus 3/4 over x minus 5 plus 1/4 over x minus 1. That right there is equivalent to what we started with. If I graph this versus any one of these previous two equations that I've got here, the original or this one in the quotient remainder form, all those are the same. Doesn't matter which one I integrate, I'm going to get the same result. So we're going to integrate the simplest one. That was the whole point. Simplify it, then integrate it. All right, we're pretty good at integrating at least the first part of this now. Integral of x is 1/2 x squared. The integral of 3, of course, is 3x, so it's a minus 3x here. Here, this is a logarithm. So the 3/4, remember, stays out front. ln of the absolute value of x minus 5. And finally, 1/4 ln of the absolute value of x minus 1. Let's see. And we are done. That right there is our definite integral. All right, that's how we deal with improper algebraic fractions. All right, let's look at some variations now that we can run into. The examples we've seen so far have been dealing with linear factors. Whenever you have a linear factor, that is the denominator is linear for these simplified fractions, you're always going to use just a constant for the numerator. You're going to find out that you end up with a constant. And that doesn't matter whether it's repeating or non-repeating. You end up with always a constant there. If it turns out that when you factor the denominator, you end up with a quadratic that doesn't factor, it's unfactorable, then the numerator has to be a linear expression. In other words, the numerator is always the degree 1 less than the denominator is really what we're saying here. And if it turns out that you have repeating factors, then the way we deal with that is we're going to actually have to use n fractions, where n is the repeating power there. If it's squared, we'll have 2 of these. Cubed, we'll have 3 of these, and so forth. You'll have n fractions whose denominators increase in power from 1 to n. So we'll have 3 fractions. The first one will be raised to the first power. The second one will be raised to the second power. The third one will be raised to the third power, and so forth, depending on what the repeating factor is, what degree it has. All right, so let's take a look at a couple of examples here. What happens if we have repeated linear factors? So on page 464, they give us this example here. It's very nice. They've already factored this here for us. The denominator, that is. That's all I need to factor. But I can see that it's repeating because of the fact that there's an x minus 1 and it's squared. So that's what tells me that's a repeating factor. So for the moment here, let's just kind of abandon the integral. We'll come back to that at the end, and let's figure out what do these numerators have to be. It's already factored, so I can write this in its partial fraction decomposition form. I know that, let's go ahead and write the original. X squared minus 4x plus 18 divided by x plus 4 times x minus 1 squared. I know I can rewrite this as some number over x plus 4 plus some number over x minus 1. And this is what we talked about on the previous slide there about repeating factors. Since this x minus 1 is squared, I need 2 of these fractions. The first one will be raised to the first power, that denominator. The second one will be raised to the second power, and so forth. If it was raised to the third power, I'd have a third one of these. The fourth power, a fourth one. Now, it turns out that you can actually still use your cover-up method, that shortcut method, to find 2 of these numerators. Turns out that you can find this numerator, that's going to be this guy right here, and I can find this whole numerator here, raised to the second power, this guy right here. It's the one in the middle that I'm going to have to do the algebraic technique to come up with it. But I'll simplify this quite a bit if I first find out those numerators Then there'll just be one unknown to solve for. Make this a lot easier to solve versus a system with three unknowns, which is where we're at right now. I don't know three of these numerators, all three of them. All right, so let's use the cover-up technique. So I'm going to again cover up the x plus 4 right here, cover him up, and plug in a negative 4. So you might want to grab your calculator just to make sure that you're doing your calculation here correctly. But when I plug in a negative 4 in the numerator, negative 4 squared would be 16. Minus 4 times a negative 4, that would be another 16. 16 and 16 sounds like 36. And then plus 18. 36 and 18 is what? 54 it sounds like. So this is going to be 54. I'm going to write that down. Divided by something. And in the denominator, again, when I plug in a negative 4 in the denominator, negative 4 minus 1, that sounds like a negative 5. And when I square that, negative 5 squared sounds like 25. Double check to make sure that we got that right. In the numerator, you get negative 4 squared is 16. And negative 4 times a negative 4 would be another 16. 16 and 16 is 32. Oh, I did that wrong. I don't know what I did, how I added that wrong before. But 16 and 16 is 32. Plus 18 sounds like 50. Okay. I was thinking I was supposed to end up with a nice number here, and I got 54 over 25. 50 over 25 turns out to be equal to 2. All right, so there's our first numerator. Again, grab your calculator here. I'm trying to do it all in my head. Now for the one on the end, what I'm going to do is plug in a value of 1. If I plug in a value of 1 here, that would make this 0. So I'll cover this up first, and I'll plug in 1. I'm a little bit better, I think, plugging in 1, hopefully. We'll see. 1 squared is 1. Minus 4 times 1, that's 1 minus 4 is a negative 3. Plus the 18, negative 3 and 18 is 15. So I'm going to write that down. 15 divided by something here. In the denominator, I'll have 1 plus 4, that's 5. I guess I could have just plugged that in right away, but oh well. I already screwed up the first one, so let's make sure we get it right. So there we go. We have, this is really just a 2. I'll cross these guys off because we were just using that to help us do the math right. I've got 2 over x plus 4, and I've got a 3 over the x minus 1 squared. Now I've got to find out one unknown here. I still don't know what this value is right here. I'm going to call him a. Unfortunately, this requires that algebraic technique here in order to come up with that a. But the good news is we only have one unknown. So let's go ahead and use that algebraic technique. We're going to multiply by this denominator. Remember, that's how we get rid of the whole fraction here. All the fraction will be gone. So when I multiply everything by this x plus 4 times x minus 1 squared, I'll be left with just x squared minus 4x plus 18 on the left side. Over on the right side, when I multiply this by the x plus 4, that will cancel that out, and I'll be left with 2 times x minus 1 squared. All right? In the middle fraction here, when I multiply him by an x minus 1. Now, there's actually an x minus 1 squared we're going to multiply by, so I'll still have another x minus 1. I'll actually be left with a times x plus 4 times an x minus 1. And finally, when I multiply this last one by the x plus 4 times x minus 1 squared, the x minus 1 squareds cancel out completely, so you'll be left with just the 3 times x plus 4. Again, go through and double check to make sure you get those multiplied out there correctly and you get the right remaining factors in here, but that's what we should end up with. That gets rid of all of our fractions. That's nice. The left side of this, just like we did before, will stay the same. In fact, we aren't going to mess with it at all from here on. The right side is what we're going to play around with. I need to actually multiply these things out here. So let's square this out first. We'll do this in a couple of steps, but you could distribute the 2 through as you go if you're comfortable with that. X minus 1 squared becomes x squared minus 2x plus 1. Remember, that's got 3 terms there when you square that binomial. Here we've got an a times, we're going to have x squared. There'll be a positive 4x and a minus 1x, so that's a plus 3x. And then I've got 4 times a negative 1, so that's a minus 4. And finally, I'll go ahead and distribute the 3 through here. I've got 3x plus 12. Left side stays the same. Distribute your 2 and your a through here. So I've got 2x squared minus 4x plus 2. I've got ax squared plus 3ax minus 4a. And then finally, the in stays the same, 3x plus the 12. All right, the next step is to do the same thing we did with the previous example there in the first half of this, which was combine all your x squareds, combine all your x's, and then combine all your constants. So for x squared terms, maybe I'll underline these so I don't miss them. I've got an x squared here and an x squared here. So I've got 2 plus a x squared. And then I've got a minus 4x, a 3ax, and a 3x. When I combine those, I've got a negative 4 plus 3a and plus 3. That's times the x. And then finally, the constants that are left, I've got 2, I've got a minus 4a, and a 12. So 2, minus 4a, and 12. Just make sure you got them all written down there. Double check to make sure you got everything there. All right. Now, I've got a quadratic over on the left. I've got a quadratic that I'm saying it's equal to over on the right. The only way these two are equal to each other is if the coefficients are the same. Now, since there's only one unknown here to find, pick the easiest one to work with, which it looks like the x squared is the easiest. And that is, I've got a coefficient here of 1x squared. That's got to be equal to this coefficient of 2 plus a, x squared. So I can set those two equal to each other. That 1 must be equal to 2 plus a. And it won't matter which one of these you pick. You could pick the linear, you could pick the constant and set those equal. You'll still come up with the same solution here. But this is obviously the easiest one to solve for. Subtract the 2. So a is a negative 1. So if I go all the way back up here, a is a negative 1. That's what we found. All right, let's go back and now answer the original question. The original question was to find the integral of this. We've now simplified it, so let's rewrite it in its simplified form and integrate it. So here's what we have. We have the integral of, it was 2 over x plus 4, plus it was a negative 1 that we just came up with over the x minus 1. And then it was a 3 over x minus 1 squared. All right. You might want to rewrite that last one here. In fact, I'm going to go ahead and do that. You have 2 over x plus 4. If you wanted to pull the 2 out of the numerator, if you prefer doing that, you could. And even with the negative 1 with this next one, you could do so. But I'm going to leave it just like it is. That's how we've been dealing with it. But the last one, I think I'm going to write that as a power function. It might be a little bit easier if we see it that way, that this is really 3 times x minus 1 to the negative 2. We're going to integrate that using our power rule. All right, let's give it a shot here. Again, the first one is a logarithm. It's 2 times the ln of the absolute value of x plus 4. Second one's a logarithm, minus that negative 1 that's in the numerator, ln of the absolute value of x minus 1. And the third one, well, this is just a power function, like we said. So integrate him. The 3 stays out front. I'm going to add 1 to the exponent, so it's going to be x minus 1 to the negative 2 plus 1. That's a negative 1. And I have to multiply by the reciprocal of that out front. I guess I'll write it as 1 over negative 1, so you can see that it's the reciprocal of it. But that's, of course, the same as a negative 1. And, of course, we have our plus c. I guess you could leave it that way. Maybe I'll rewrite it one last time here just to clean up that constant in the very last term there that we had. First 2 terms here will stay the same. So you actually got 3 times a negative 1 there. So that's really a minus 3 times x minus 1 to the negative 1. If you want to rewrite that as a fraction, maybe that's the way to do that. So I'll write that as minus 3 over x minus 1 plus c. By the way, you don't have to rewrite it. The previous step there was perfectly fine to leave it in that form, actually. But there's our answer. All right, let's take a look at one last example here. What happens if these are quadratics that don't factor? Like I have an x squared plus 1 here in this one. So non-repeating, unfactorable quadratic. How do we deal with that? Well, for the moment, again, we're going to abandon the integral, and we're going to deal with just reducing this fraction, the partial fraction decomposition, that is. So let me rewrite this. All right. It's already factored for us. That was nice of them. So I can rewrite this as some number over x minus 2 plus some number over x squared plus 1. And actually, I say some number. Your quadratics have to have a numerator that's linear. So this is going to be actually ax plus b is what we're going to have there. It's some linear. It's not just a. It's got to be a linear. So it's some number times x plus some other number there. Now, I left off the x minus 2 numerator because we can use our cover-up method to come up with that. In fact, let's try that out. Let's cover up the x minus 2, and we're going to plug in a 2 and see what we end up with. When I plug in a 2, I'll have 7 times 2 squared. 7 times 4 is 28. Minus 4 times 2, that's 8. So 28 minus 8 is going to give me 20. And in the denominator, I end up with 2 squared is 4 plus 1 is 5. So I end up with 20 over 5. That's 4, right? So the numerator there is 4. Again, if you can help yourself out by finding one of the unknowns using that cover-up method, do it. That'll save you some work here later on. But unfortunately, to come up with the a and the b, we got to go through the same process that we just did. So let's do that. Let's get rid of the fraction first by multiplying through by this denominator. So I'm going to be left with 7x squared minus 4x is equal to 4 times, it's going to be the quadratic that I'm left with here. I'll have ax plus b. This time the quadratic cancels out and I'm left with the linear x minus 2. And again, you should catch on that the left side of this is staying the same as we go through this now. 7x squared minus 4x stays. Distribute the 4 through here, so we get 4x squared plus 4. Multiply this guy out here. You'll get 4 terms when we do that. I've got an ax squared. I'll end up with a minus 2ax. I'll end up with a bx and a minus 2b. Again, left side stays the same. Right side, combine like terms. So find your x squareds, find your x's, and find your constants. So I've got a 4 plus a x squared. That's going to make it real easy to find out what a is equal to, because there's only an a in that part. For the x's, I've got about a minus 2ax and a b, right? So plus a negative 2a plus b times x. That involves both a and b, so I'd have a system to solve there if I'm going to go for that. And then for the constant, I've got a 4 and a minus 2b. Which, since that only involves one variable, that's going to make that really easy to solve for. So let's check out what we got here. I know that the 7x squared has to be the same as the 4 plus ax squared. In fact, we can go ahead and write that out here and figure out what a is equal to right away. 7 is equal to 4 plus a. Subtract the 4, so 3 must be our value for a. Now that you know a, I guess you could technically use this middle term if you wanted to, but I'm going to suggest we use the constant. Now when you look on the left side here, you're going to go, wait a minute, there's no constant here. That means that's really a plus 0, right? That's what this has to be equal to. So 0 is equal to 4 minus 2b. I guess that means 2b, I'll move that over since that makes it positive here, is equal to the 4. Divide by your 2, so b must be equal to 2. There we go. I've got my a and my b. And now we're all set here to go back and answer the question they asked us. We've now simplified this problem from the original integral they gave us to this one. We now can rewrite this as, we figured out it was 4 over x minus 2. We figured out that numerator with our cover-up method. And then we just figured out a and b were the 3 and the 2. So that would be 3x plus 2 over this x squared plus 1. All right, the first part of this we're good with. We know how to integrate 4 over x minus 2. The second part we got to deal with If that was a u substitution that would work there, I would use that on that and be done with it, but that's not going to work here. So we're going to split that second fraction up here. I've got 4 over x minus 2. And think of kind of undoing when we add fractions together, combining rational expressions. I can rewrite this as just 3x over x squared plus 1, and then plus 2 over x squared plus 1. It's kind of the opposite of how we think of combining rational expressions. Normally we have a common denominator and we add those together. We've now separated them is really what we've done, but still the same as what I've got at the very beginning. All right, so the way we're going to integrate this, again, the first term is all good. That's a logarithm. The second term, this looks like now a u substitution that I could use here on this. That, in fact, maybe I'll rewrite this as 3 separate integrals just so we can break it up that way. I've got the integral of 4 over x minus 2 dx plus the integral of 3x over x squared minus, or x squared plus 1 dx. And then plus the integral of 2 over x squared plus 1 dx. I'm just breaking that up using my properties of indefinite integrals. All right, this middle one looks like a u substitution. If I was to make u equal to the denominator, x squared plus 1, then d would turn out to be 2x dx. I have a 3x dx in here, so I guess I could either pull the 3 out front and deal with that, or if I want to actually get a 3x dx, I could multiply both sides of this by 3 halves, right? If I take 3 halves of du, I'd end up with a 3x dx. That looks like a nice way to do that one. And the last one, well, that one you might have to go back and refresh your memory a little bit, but we've seen that guy show up before. That if I have something over x squared plus 1, this thing here turns out to be an inverse tangent function. I don't have to really do anything with it. This is really inverse tangent of x. So we are all set to do some integration on this. So what do we have here? Again, the first part of this is going to be 4 ln of the absolute value of x minus 2. If you actually want to do the u substitution like we said there and then evaluate this, that might help you with this next step here. But the middle part of this turns out to be 3 halves the ln of the absolute value of x squared plus 1. And again, the last part of this, I got to recognize that that's my inverse tangent function when I integrate that. The 2 in the numerator just stays out front, so that's 2 tangent inverse of x plus c. Go from something that we can't integrate to something that we can integrate. That right there is the end of the second half here of section 9.7.